This is ELEC142 Semester 2 Problem Sheet 4 Solutions Part 2. So this is all about, again, dealing with compressing a series of capacitors, resistors and inductors into a single complex impedance, so we can replace all of this with just one block of resistance which has a real and an imaginary part. And this is really helpful because it really simplifies what we're trying to do, so we can perform more complex analysis. So let's have a look and see. Let's try and solve question 5. So previously we've looked at just resistors and capacitors, or just resistors and inductors in series and in parallel. Now we're going to combine capacitors and inductors in the same question. So let's have a look and see. So this is going to get a little bit more convoluted, but not that much more difficult. You've just got to be a bit careful to make sure you don't confuse yourself. So let's have a look at question 5. So again, you can see my working is getting a little bit longer here, so I can just about fit it all in the same screen. What have we got? Well, I've redrawn my circuit here with my 20 picofarad capacitor, which is in parallel with a series combination of 75 ohm resistor and a 8 millihenry inductor. So by looking at this, we're just going to break it down into smaller steps so we know where to begin. So step 1, as we've always done, is we're going to calculate the reactances of all of our components that we're using. So first up, our resistor remains the same, so that, written in full rectangular form, is 75 plus 0j ohms. First part done. Next up, we've got our inductor. Doesn't matter which order you do these in, I just fancy doing the inductor next. So the reactance of the inductor is j omega L. So we've got j, put in our omega value, which was 500, which was given at the start of the problem sheet, times L, which is 8 millihenries, so that's 8 times 10 to the minus 3. What we get out here is going to be 4j, so to write that out in full rectangular form is 0 plus 4j ohms. So, good. So now to finally do our capacitor, the reactance of the capacitor is minus j 1 over omega c. So we're going to put the numbers in. Omega is the same, it's constant, that's what our supply is working at. And then we put in 20 picofarads, so that's 20 times 10 to the minus 12. If we put this out, what you get is minus 1 times 10 to the 8j. That's what you'll find. And because we've got no real part, we just need to put that 0 in front. So our full rectangular form is 0 minus 1 times 10 to the 8j ohms. So that's all the reactance is done. Next up, we're going to have to simplify our circuit in 2 steps. We can't do it in one like we did previously. So our circuit is going to go from this form, into this form here. What we can see here is we're not interfering with the capacitor for now. We're leaving that. We're going to deal with that in the next step. The bit we're interested in is this section here. What I've done is I've combined the resistor. Let's draw it this way and we'll see. So I've combined the resistor and the inductor into a single impedance, which is ZRL. I've just decided to call it that. And what we can see is that ZRL is equal to the reactance of the resistor plus the reactance of the inductor, because those two are in series. That's what I've done here. This is the same as we did for the series components in questions 1 and 2. So I've just got the rectangular form, I've added them together, and you end up with an answer of 75 plus 4j ohms for that part. I've gone over that quite quickly because that is quite simple. We've done this to death in the earlier parts of the question. So now we've got to this stage where we have our value for ZRL. So now we can see that we have 2 complex impedances in parallel. So what we can do now is we can combine those in the parallel form like we did for the parallel questions of 3 and 4 in this problem sheet. It might seem more complicated because ZRL has both a real and an imaginary part, because it's 75 plus 4j ohms. That doesn't matter. The process that we perform is the same. We just need to be a little bit more careful with our mathematics. So now we're going to go into this form. We're going to end up with Z total. So I've just said Z total is equal to the reactance of that capacitor in parallel with the impedance ZRL, which we calculated in the previous step. So what I've done is I've put those numbers in here. It's exactly the same, so we've got the product on the top and the sum on the bottom. This is XC, this is XC on this side, so this is the capacitor value, which we calculated at the beginning, and this is ZRL, which we calculated just a moment ago. So for the top, because it's multiplication, we need to convert these to polar form. So I've just done that on my calculator. So you should get some values along these lines. So the first one is quite simple because it's a pure capacitance. So it's a magnitude of 1 times 10 to the 8 at an angle of minus 90. The 75 plus 4J I recommend you do on your calculator because it's not as simple. So this we can find is actually a magnitude of 75.1 at an angle of 3.05 degrees. It's the first time we've looked at something at this stage which isn't plus or minus 90 or 0 degrees. And the reason is because we have both a real and an imaginary part. So for the bottom, because they're both in rectangular form, we can just add them directly together and we get this value where we can see that the value of J is much bigger than the value of the real part. That's just because looking at it we can see the difference in these scales of magnitude of these numbers. So next up, what have I done? I've done that phasor multiplication, so we multiply the magnitudes and add the angles, and that's what we get. And the bottom part I've just converted into polar form, and you can see once again that because the magnitude of the imaginary part was so much bigger than the magnitude of the real part, this has become, it's just completely dominated it. So it's this massive magnitude at an angle of minus 90 degrees. You can do that on your calculator, but that should make sense. So it's important that you can look at your working and then look at the answer you get from your calculator and make sure that it's sensible. Don't just trust what your calculator says, make sure it is reasonable. So well, next up, let's just do that phasor division. So you divide the magnitudes and subtract the angles, and you get 75.1 at an angle of 3.05 degrees. So you can have that answer, or you can convert it to rectangular form, which gives us a final answer of 74.99 plus 3.996 J ohms. That's the answer. So once again, you can see this isn't part of the question, this is just a bit of a further explanation, is that this final answer here is incredibly similar to the value of ZRL, which was our combined impedance of our resistor and our inductor. And once again, for similar reasons to question 4, it's because at the frequency we're operating at, this capacitor value is very small. So the main contribution to the impedance comes from this branch, which is ZRL. Just a side note really. And once again, please be very aware that this will change with frequency. This is the answer for the operating frequency given at the start of the problem sheet. So that's question 5. Let's look at question 6. So we can see a lot of similarity between this question and the one we've just solved. So in fact, all that's changed is we've swapped the position of our inductor and our capacitor, and the value for the capacitor is different. The value for the inductor is the same. We just want to mix things up a little bit. We don't want to make it too easy for you. So let's have a look at solving this. So as you can imagine, the procedure is going to be practically identical. So let's run through that and check what you've got. So, question 6. So I've redrawn my circuit. I can see that first up we're going to calculate the reactances of each of those components and present them in rectangular form. So the value of the resistor is 500 plus 0 J ohms. The reactance of the inductor is 0 plus 4 J ohms, same as we had before. And the impedance of the capacitor is 0 minus 6.67 times 10 to the 5 J ohms. So again, that's quite a significant number. So that's the first part. We found the reactances. What we can see now is we're going to start to simplify our circuit. So that was laying the groundwork. If we look, what we can see is we're going to move down. We're going to leave that inductor alone for the moment. We're not interested in that. First of all, we're going to deal with this part of the circuit, which you can see this branch is the series combination of that 500 ohm resistor and that 3 nanofarad capacitor. Nano is times 10 to the minus 9, just in case you can't read that clearly. So please make sure you've got your indices correct. So we can join these together, a series combination, and replace them with one impedance block, which I've called ZRC. So to calculate that, we can just see we add those two values together, and what we've got is the rectangular forms. I've just put them in, and it gives us a final answer of 500 minus 6.67 times 10 to the 5 J ohms. So far so good, that was dead simple. Next up, we're going to do the next step. So we can see now that we've got a parallel combination of our inductor, our inductance, our complex reactance, XL, in parallel with our complex impedance ZRC. It's worth saying this is only true when we've converted to our complex impedance. We must be in ohms, otherwise this doesn't work. So I've replaced 8 millihenries with XL. That's the only reason we can do it. So let's do that parallel combination. Z total is equal to XL, the impedance of the inductor, in parallel with ZRC, which is the impedance of that resistor-capacitor series combination. So I've just put these values in. So we've put XL here, that's the inductor value, and then this is ZRC, which we worked out in the previous step. And as before, we've got the product over the sum. So I've done the previous step. So what I've done for the top part, I've converted it to polar form because we want to do that multiplication. For the bottom part, I've just added the rectangular forms together. Next up, I've done that phasor multiplication. I'm not going to go through how to do this. You should be able to do this by now, so I'm not going to laboriously tell you every step. Bottom part, I've converted to polar form, so I can do this phasor division. Phasor division is done then, and what you get is 0.4 at an angle of 90 degrees, or thereabouts, which in rectangular form converts to 0 plus 0.4 J ohms. So there we go. That's the final answer for that bit, which is interesting because it becomes really dominated by that inductor, because we've got no real part and we've got that part is contributed, it's plus J, so that is an inductance value. If it was minus J, it would be more dominated by the capacitance. So that's the answers to questions 5 and 6. Hope you got those right.